AP Chemistry, this is the answers video for day 90, Le Chatelier's principle. And let's go ahead and do this. Okay, so what Le Chatelier's principle says is that if a chemical reaction in equilibrium is somehow thrown out of equilibrium, either in terms of pressure, temperature, or concentration, it wants to try to return to its equilibrium state. So we're going to take a generic reaction. 2A plus B produces C plus 3D. It's an exothermic reaction. It's giving off 32.4 kilojoules of heat. So you can treat heat as though it's a product. You can put it over here as a plus heat on the right side because the heat is coming out. All right, so let's look at this. Concentration of A is increased. So you're increasing the concentration of this. That means this side of the equation is more crowded. So you're increasing the amount of a reactant. That makes this side of the room, this room, more crowded, and so the people want to move over to this room over here. So the reaction moves to the right, and we say, first of all, you can draw an arrow to the right, and the term is that you want to become familiar with is favors products. It's moving on the side of the products. Okay. Next, the concentration of C is increased. Here's C on the product side, so that's making this side of this room more crowded, so it wants to move back. The people want to move to the less crowded room, so they're going to move backwards. So that's an arrow to the left, and that favors reactants. Now, you don't have to have both of the reactants increase in order for it to flow to the right, just one of them. Or same with product. You don't have to have both of them increase to flow to the left, just one of them. Okay, concentration of D is decreased on this side, so it makes this room over here less crowded. You've taken some of the D out. That means that people want to move to the less crowded room. So at this point on, I'm just going to draw arrows. So that's going to favor the products. You should write the word favor products though. Okay, now the temperature is increased in the reaction. So this one, heat wants to come out. Now it means the temperature of the surroundings. Okay, that should be clear. It's the temperature of that the reaction is taking place in. It wants to give off heat, but if you increase the temperature outside, you're shoving heat back into the reaction here. And so that's going to slow the reaction moving from left to right. So let's think about that. Let's say this is putting off heat in a cold room. It'll be very easy for the heat to go from the higher temperature of the reaction into the cold room. But let's say that room is 1,000 degrees. And let's say this is putting out an amount of heat equal to 200 degrees. And this is 1,000 degrees pushing back. Then the heat is going to flow from the room back into the reaction. Or think of it in terms of a heater. A heater is at 200 degrees. The room is at 20 degrees. Then the heat is going to flow out of the heater and into the room because it's higher temperature to lower. But what if the room is 1,000 degrees? Then the room at 1,000, the heater at 200, the heat is going to flow into the heater. It's going to flow backwards into the heater because that's the lower temperature. So that's what's happening here. If you increase the heat of the surroundings, it's going to push the heat back into the reaction, and that means it's going to favor reactants. It's going to flow to the left. Temperature is decreased. Okay, that means you made the room outside colder. It's much easier for the heat to flow out, so that's going to increase products. Now that's for an exothermic reaction, one that wants to give off heat. All right, come down here. We have 2NO2 produces N2O2. So concentration of N2O2 increases. This side becomes more crowded. It moves back, so it favors reactants. Concentration of N2O2 is decreased, so this room becomes less crowded, so the people want to move over there, so that favors products. Concentration of NO2 is increased, so you're making this room more crowded, so they want to flow to the right to the less crowded room. Favors products. Concentration of NO2 is decreased. That makes this room less crowded, so the people want to flow back to the left. That favors reactants. Temperature is increased. Again, it's an exothermic reaction, so it wants to give off heat. You can write that right here, plus heat. Okay, so if you increase the temperature outside, it's going to be harder for the heat to get out, so that is going to favor reactants. It's going to push it back. If the temperature is decreased, then the room becomes colder. It's easier for the heat to get out, so that's going to favor products. Now pressure, it has to do with number of moles. So here's the situation. If the pressure is increased, it means you increase the pressure. So listen to this, follow the sequence. Okay, you increase the pressure. How would you do that? Maybe by squeezing the volume down. So you increase pressure. The reaction says, I don't want my pressure increased. I want to go back to my old pressure. So the reaction wants to decrease pressure. Okay. So the reaction says, the reaction doesn't have any control over volume or temperature, but it has control over one thing, and that's the number of moles. Okay. And it wants to decrease the pressure. It knows if it can reduce the number of moles, it'll reduce the pressure. If it can cut the number of moles in half, for example, it can cut the pressure in half. Now, it may not want to go that far, but it wants to reduce it, okay? So it's going to want to go, if it wants to decrease the pressure, it's going to want to go in the direction of fewer moles. So it's going to want to go from the 2 mole side over to the 1 mole side. And that's going to favor products, okay? So it's not about favoring products, it's about favoring the side that has the fewest moles if it wants to decrease pressure, okay? So reaction moves to the side with fewer moles. If its pressure is increased, it wants to go back to decrease it, and to decrease it, it goes to fewer moles. So in this case, that would favor products in this case. If the pressure is decreased, it's just the opposite. You decrease the pressure, the reaction says, I want my pressure back up to where it was before. So it's going to go to the side that's going to create more moles, so that's going to move from right to left, that's going to favor reactants. All right, and that's how Le Chatelier's principle works. Okay, next question says, explain briefly how a catalyst affects the rate of a reaction and the equilibrium of the reaction. So this goes back to kinetics. So let's go ahead and write out the answer. Okay, so a catalyst speeds up a reaction by changing the reaction mechanism. That's the wording that was used in one of your Princeton questions. But what this usually means is lowering the activation energy. Okay, so remember, the activation energy is a hill that the reaction has to get over with its own kinetic energy. So that's how it usually does it. Now, this is the key to this. This is why I asked this question in the equilibrium unit. The catalyst does not change the equilibrium. You start off with a certain amount of products, you're going to end with a certain amount of reactants at equilibrium. The catalyst only affects how fast that takes place. It does not change the equilibrium. It does not change the concentration of reactants or products. Okay, let's move on to the next one. Now, there was an error in the video, so let's define a few points here. There was an error in the lecture video. All right. So let's define what solubility product is. It is the equilibrium constant for a dissolution reaction. So it's Ksp. It's how much is that reaction going to move from reactants over to products. Molar solubility, an incorrect definition was given in the lecture video. So molar solubility is the amount of the compound, that is the solute, that dissolves until the saturation point is reached. So basically that's the equilibrium point when it hits the saturation point. What is saturation point? Saturation point is how much of a solute can be dissolved before there are no more free water molecules to dissolve anymore. Okay? So you basically run out of water molecules to continue to dissolve it. So what happens to it then? It'll just sink to the bottom as a precipitate. All right, so those definitions are the main ones you need to understand solubility product. Okay, so let's go ahead and do this. So, generally in these kinds of problems, you're going to be given a solubility product and asked to figure out the molar solubility, or you're going to be given the molar solubility and asked to figure out the solubility product, okay? So it says the Ksp value for lead chloride is 2.4 times 10 to the negative fourth. What is the molar solubility of 0.2 molar PbCl? Well, the concentration initial doesn't matter, and you're going to see why in a minute. Let's go ahead and put it in here. It's 0.20 is the concentration of the lead chloride. And now it's going to, since the coefficient here is 1, it's going to lose some of it. Now the S is for solubility. You could use X. If you don't like the fact we changed letters on you, you could call it X, okay? Minus X. So down here, it's going to be 0.20 minus X. Now you start off with none of the product here. And now this coefficient is 1, so it's going to be plus 1S. Just call it S. And this coefficient's 2, so it's going to be plus 2S. So 0 plus S is S. 0 plus 2S is 2S. Okay, now let's write the law of mass action for this. It's based on these. The ions don't have any effect on this problem. It's just Pb2+. But the coefficient there becomes the exponent there, and so that's the law of mass action. So again, because we talked about, because this is a solid, it is not a part of the law of mass action. That's why I said that the initial concentration doesn't matter. You can just X that out altogether. What we want to know is the molar solubility, which is this, but this is also this. Okay, it's S. Whatever S is the answer we're looking for. Okay, so now let's plug in our variables and our numbers. So Ksp. Pb is S, the concentration at equilibrium. And Cl is 2S right there, and then you have to square that. So if you do the math on that, you get S times 4S squared, and you multiply the S by, and you end up with 4S to the third. That's math, not chemistry. All right? So 4S to the third equals 2.4. Let's just rewrite it down here. Okay, we're going to divide both sides by 4. And I'm going to move the S third over to the left side of the equal sign. S to the third equals 0.6 times 10 to the negative 4. So now we got to figure out what S is. You got to take a cubed root. So you're going to take the cubed root of both sides, like that. So cubed root of S to the third, and you got to write a 3 there for a cubed root right there. So that's going to be S. Now what's the cubed root of this? Let me show you how to do that on the calculator. Okay, so the first thing to understand is a principle of math. The cubed root of any number or variable is equal to that variable or number to the 1/3 power, to the reciprocal of that. That's how you would do a cubed root, all right? So what this is going to become is, this is going to become this. And you're going to raise that to the 1/3 power. And that will give you your value of S. So let's do that on the calculator. Okay, watch how I do it. You got to watch out for the parentheses. So parenthesis 0.6 times 10 caret negative 4. And now I'm going to close the parenthesis. And now I'm going to raise that to the power of 1/3. So I got to open a parenthesis here. Be careful. If you don't do that, the order of operations is going to get messed up. And I'm going to do 1 divided by 3, close the parenthesis. So it's raised to the 1/3 power, and that gives us 3.9 times 10 to the minus 2. You write it as a decimal or scientific notation. So it equals, okay, and it is a molarity, it is a concentration, so it should have an M coming after it. Okay, that's how you do that one. Okay, final problem here. Actually, second to last. The molar solubility for manganese carbonate is 4.2 times 10 to the minus 6th molar. The initial concentration is 0.3 molar. What is the solubility product, the equilibrium constant for solubility for that? Okay, so it says first write the reaction. So you go to your charge number by ion sheet and you find out there's two different charges for manganese. Carbonate is always a 2-. You get that from your 60 common ions. So since it's a 1-to-1 here, it's going to be manganese 2+. If it were the 4+ version, you'd put this in parentheses and put a 2 out here because you need 2 of the 2- carbonates, but it's not, it's 1. Okay, plus the carbonate, CO3 2-. So 2+, 2- balance. And I should put aqueous, they are dissolved. Alright, so that's what the reaction would look like. Write the law of mass action. Again, you don't include the solid, so it's going to look like this. Okay, and again, it's aqueous, aqueous. Okay, so coefficients of 1, so that's what it looks like. Alright, so let's write the reaction here. And I always like to write arrows in Rice tables so I don't forget which side is reactants and which side is products. Okay, so the initial they give you is 0.3, but as in the last problem, it really doesn't matter. And it's a coefficient of 1 here, so it's minus S or X, whatever you choose. 0.3 minus S. And then you always start with nothing here. Usually you do. What happens if you don't? We'll talk about that at a later time. Okay, now you're adding coefficient of 1, coefficient of 1, so it's plus S. So this becomes S, this becomes S. So this S goes into Mn, this S goes into CO3. We don't even need this. We do want, we want to know the Ksp, so we're going to go ahead and do this. Because we know what S is, it tells us. It tells us that the molar solubility is 4.2 times 10 to the minus 6. Okay, so now we're going to plug our algebra variables into our law of mass action. So S goes in for Mn2+, and this S goes in for the carbonate right there. Alright, so that's going to be S squared, but we know what these values are. It's 4.2 times 10 to the negative 6th, and so is this one. So that's going to be 4.2 times 10 to the negative 6th squared. Okay, so let's do that on the calculator. Be sure to know how to do that. So I'm going to start with a parenthesis, caret negative 6, close parenthesis, and now I'm going to hit the x squared button right here. Just hit the x squared. And hit equals. And we get 1.76 times 10 to the negative 11th. You can see that. And since it's an equilibrium constant, it has no units of measure. So there, that is your answer. All right, now I'm asking you to go back to day 15 video and write the definition of an ionic bond. Write it completely as it's found at minute number 8, and be sure you're clear on how an ionic bond is formed. All right, that takes care of this answers video.